Okay, so now we are streamed, but people are still coming, so let's wait a bit. So do you hear me okay, or is there really a connection problem on my side?
I can hear you fine.
Okay, hi Nick. I make you co-host. Welcome everybody to today's seminar. We will today have two speakers, Amir Dembo and Nick Cook. And Amir will start with a talk on sparse random graphs with unusually large subgraph counts. As always, if you have questions, you can write them either in the chat or you can unmute yourself and ask questions. Okay, Amir, the screen is yours.
Okay, thank you very much, Nina, for organizing the seminar and for introducing me. I will talk on sparse random graphs with unusually large subgraph counts. This is based on joint works with Nick Cook, Yui Pam, and Soham Bhattacharya, and Nick will give a follow-up lecture on a related topic to which I will refer during my talk as well. So let's start with the first motivation for this kind of study. And there is interference on the line by someone.
Yes, I heard it. I tried to mute people. But I'm not seeing everybody.
I think you can mute everyone.
Yes, maybe I can do that. People should be muted upon entrance, but apparently not. Okay, so I will try to mute people. Okay. It seems to me that now almost everybody is muted.
I will continue. So many problems in combinatorics, that's one of the motivation, are of the form that you have a large discrete set, here called G of n, and we want to understand the behavior of some real function on this set under the constraint of another function on this set. And this talk will be about a particular case of this such a question. And we will take the set Gn will be the set of all simple graphs over n vertices. And we can think of them as a binary vector of length n over 2, assigning 1 whenever we have an edge and 0 otherwise. And in this set, the two functions we will be interested as an example are to count triangles. So we will have two functionals, t and e. One counts the number of triangles, t, and the other one counts the number of edges in our graph e. And you can write them also in terms of the adjacency matrix of the graph. The adjacency matrix of the graph mentioned here below, A of G, has entry Aij, which is 1 if I and j is an edge and 0 otherwise. So it's a symmetric matrix with 0, 1 valued. And in this notation, the number of triangles is the sum over all triplets ij and k of aij, ajk, aik. So it's a trace really of a cube. And the number of edges, you can also write it as a total number of terms in the matrix or the number of edges in the graph. These are also special cases of what is called subgraph count. And I will use by script n with the subset the graph H and the big graph G where you check for the subgraph count of H in G. That means you count how many copies of the graph H you can find inside the graph G. H will be a finite graph of finite size, and G will be a graph of size going to infinity. In particular, triangles are the complete graph of 3 vertices, denoted by K3, and edges is a complete graph of size 2, denoted by K2. So I'm interested in we will be interested in extremal combinatorics. One may be interested in maximizing T of G, the number of triangles, over all the graphs with a specified upper bound on the number of edges. The upper bound on the number of edges here is important because if you do not put it, then of course a complete graph will have the maximum number of triangles and the problem trivializes. So you're interested in graphs which manage to do a lot of T under some constraint of E. So that's the extremal problem in combinatorics. We will not go that direction. Probabilists, on the other hand, will typically study the typical behavior. Typical behavior means you choose a graph G in some ensemble of graphs. And the most common ensemble for probabilists and also for combinatorialists is the Erdos-Renyi random graph on the set of vertices n with a parameter p. That means that you choose each of the edges independently and identically distributed with a probability p between 0 and 1. And when you do that, the number of triangles and also the number of edges are going to be a sum of many independent or nearly independent things, so they will concentrate extremely well around their expectation. You can easily calculate the expectation. For example, the expected number of edges is just going to be n choose 2 possible edges, each one appearing with probability p. Here I called it m. Number of triangles is similarly n choose 3 possible ways to choose your I, j, and k, your triplet in the vertices. And then you want to look for a copy of a triangle, and that will cost you p to the q because you need all 3 edges to be present. So you can calculate, you can say, well, E of G is going to be concentrated on n choose 2 times p. Let me call it m. I can isolate p out of this equation, plug it in the formula for the expectation of the number of triangles, and I know that typically the number of triangles will grow like some function of n and m being my constraint and n being the size of the graph. So that's the opposite of extremal behavior. I look at a typical behavior. In between, we can look at large deviation. Large deviation is sort of a soft extremizing. We will look at graphs which will achieve a larger value of t. That is, we will look at the set, let's call it t k3 of delta. Those are all the graph where the count of the number of copies of the triangles in the graph is exceeding its mean by a factor 1 plus delta. So in this case, it means that I take q, so q to the cube is 1 plus delta times p to the cube, and I'm looking for graphs whose value is the same as the one for Erdos-Renyi with the parameter q, even though they come originally for the parameter p. As I increase q, this will become rarer and rarer, and I'm going from the typical towards the extremal in a more graceful way, and I can use probability. What I want to know, which is closely related to the extremal problem, is to know the law of the graph if it belongs to this rare set. That is to say, what is the most likely way to achieve the unlikely event of having many triangles in a graph where essentially, because of the probability constraint, the typical number of edges is equal to m. So that's kind of a more softer version of the extremal problem. In order to understand the conditional law, my question, the answer towards it usually relies on first calculating the asymptotic tail event for the probability in question. Usually, if you can calculate accurately minus the decay of minus log of the probability of the event in question, you will understand what is the source for this unlikely behavior, and therefore what is a conditional behavior. So we will look at 2 questions in general: the asymptotic large deviation of the upper tail of this event, and the conditional law of the graph given this event. So let's look first on some results on the typical structure of a random graph, of Erdos-Renyi graph, conditioned on this large deviation event. So we have again our random graph G and P of size n, and I will denote hereafter the law of this graph by mu n P of G, that is going to be a product measure on 0, 1 to the n choose 2, assigning probability p to each of the edges. Triangle counts, and as I mentioned before, and its expectation as we learned before. So we want to condition on extra triangles, meaning the event tk3 of delta, that is a number of copies of triangles in our random graph G, exceeds a threshold, and we want to know how are the edges distributed, or what is the law of G conditioned on this event. There are many possibilities, but there are a few relatively simple yet striking ways to achieve the extra triangles, and I will go over 3 of them, and then later on we will see them appearing depending on the choice of the range of P. So one option is kind of indicated already from the notation and the parameterization. If your graph looks conditionally like an Erdos-Renyi graph with probability Q instead of P, then it will typically have exactly this number of edges. So that, or triangles, that means that you essentially just increase the edge density everywhere equally and not trying to do anything more sophisticated. That will be indicated by green whenever I have a choice. There are other ways to achieve a large number of triangles. One of them is to plant a small but large, meaning small compared to n, but large compared to 1 clique. Clique is a complete graph. So if you have a complete graph of size L, it will produce L choose 3 extra triangles. And what you can do, you can say, instead of planting my extra edges equally around all the n vertices, I will concentrate them all in a small location, getting an advantage because the number grows like L cubed instead of L, the number of triangles. So that will be indicated by the blue strategy. And there is another strategy one can think of, which is the red strategy, which is what you do. You plant a small but even smaller hub. A hub is a collection of vertices which are connected to everyone else. If you connect two vertices to every one edge, for every 2 of them, you get already a wedge, a vertex connected to 2 other vertices, and then only one random edge will close a triangle. So it's a kind of compromise between the 2 strategies. In the blue strategy, you created all the extra triangles by hand. In the green strategy, you changed everything and hoped for the typical behavior to take place. In the red strategy, you do something intermediate. And you can, of course, do something much more complicated than these 3, but you have at least 3 choices which come to mind very quickly after you think about this problem. So this was studied by Chatterjee and Varadhan in 2011. They proved the large deviation principle for Erdos-Renyi random graph. And out of it, they calculated the conditional behavior. I will go towards the end of the talk. I will start or prepare for Nick's talk by explaining briefly the ideas behind Chatterjee and Varadhan large deviation paper. And here is a drawing of the strategy which predominate in the domain depending on Q bigger than P between 0 and 1. So here Q and P are fixed, Q exceeding P, and N goes to infinity. And they calculated, and this picture is taken from, is following a follow-up work of Lubetzky and Zhao. And they calculated the area denoted here by dark blue is the area where the green strategy, that is of changing to Erdos-Renyi parameter, which is slightly larger, predominate and is a likely behavior of the graph conditional on the rare event. In question mark is a small area, and Lubetzky and Zhao analyzed the variational problem related to this large deviation, to which we will come later in the talk. And they found that this is exactly the domain where the answer is a green. The answer in the area in the question mark is unknown. It may be the clique or the hub. It's probably not. It is definitely not the green. It's probably something much more complicated. And this question mark remained open for the last 10 years. So nobody knows. The variational problem is known, but nobody knows how to solve it. And therefore, there is no nice characterization of the conditional law. We will get to that later on. I will do now a digression or a detour to Gibbs measures, and in particular to something called the naive mean field approximation. In a paper with Shurav Chatterjee in 2014, we proposed an approach to large deviation for nonlinear functions in a large space, typically in a large product space, and specifically in a large product space of Bernoulli's, which is exactly our random graph, with the intention of studying or extending the result of Chatterjee and Varadan to this more challenging sparse case, where as n goes to infinity, we take p to 0 as well. And the strategy we propose is as follows. If you want to study the large deviation of this function, what you can do, you can study Gibbs measures with density which is proportional to some Hamiltonian, which is another function from 0, 1 to the d to r. Okay, this is well known. The idea is as follows. You take E of h, you take your density as a smooth approximation of the indicator of the rare event that you are interested in. Here you want to make f very large, bigger than L, some atypical value. You have a reference measure mu star. You want to study the tail behavior mu star of all the x's such that f of x is exceeding L. If you approximate f of the indicator by e to the h, then the partition function, the sum over all x of e to the h mu star, will give you a good approximation of this probability of the indicator where you replace e of h by the indicator. So you just make smoothing calculation of indicator by moving to a Gibbs measure, and that's very well known in statistical physics and also in probability. The idea then is as follows. It is well known from the theory of large deviation, also well known in statistical physics, that the log of any partition function can be expressed as a duality problem as follows. It's a supremum over all probability measure on our discrete set of the expectation under the candidate probability measure nu of the function h, which is sitting here in the exponent, minus the relative entropy or Kuhl-Black-Leiber distance between our candidate nu, and the reference measure mu star. This is a fundamental result which is behind quite a few results in large deviations. And it is well known, this is just an equality. As it is, it doesn't really help us calculate the log of z because the soup is over a huge collection and it's actually an identity. So if you solve this optimization problem, you end up with what you started with. However, the naive mean field approximation is if you want, a postulate or a conjecture that you can try to prove that the supremum is approximately attended by product measures. In particular, if mu star, the reference measure, was already a product measure, there is a possible hope that the answer will actually be optimized over product measures, in which case the supremum will be over a much better behaved set of measures, much smaller. The Kuhl-Black-Leibler distance or relative entropy is very nicely tensorized with respect to product. And this variational problem might be much easier to solve than the original log of z calculation or the original tail probability. This is called naive mean field approximation. It is actually not very naive, and it is actually the key tool to the study of random graphs that we are discussing in these lectures. It is called naive mean field approximation because from the point of view of statistical physics, it is somewhat naive because in disordered measures, a la, for example, spin glasses, this is never going to happen. The situation is much more complicated, and the answer does not follow this principle. Anyway, we can hope to have this under a reasonable situation. This principle, that is a general formulation when is a nonlinear function f, such that when you do this approximation, you have a good chance to get a naive mean approximation. This was the study started by Chatterjee and myself in 2014, and we derived conditions. The conditions were more or less around the idea of calculate the gradient or differences of the function f and see if you can approximate all possible values of this gradient, which is going to be a long vector if d is getting very large, by some net of vectors whose size does not grow exponentially in d. And if you can succeed in doing that, then we show that you have the naive mean field approximation holds, and we applied it, and we will see later how, to study the tails of sparse random graphs, exactly the problem I started with. This idea of doing naive mean approximation was extended and refined at least in 4 works by Jan, Eldan, O'Geary, and Austin, doing different things. For example, Jan changed from the Bernoulli vectors to a more general, including Banach space alphabet. Eldon looked at our condition on the gradients, which were kind of awkward because we need to take the gradient of a function at discrete points, and we didn't do it in the most appropriate way. And Eldon used ideas from Gaussian processes and stochastic analysis to write much better conditions on the gradient and thus increase the domain of the validity of the naive Mild approximation. This was finalized or refined by O'Geary, who find optimal conditions in Eldon setting. Austin, at about the same time, taking a very different point of view, used information inequalities to rederive these ideas in a completely different manner, which allowed him even to change the alphabet to a discrete set that grows with D and still get interesting conclusions. The disadvantage from our perspective of studying number of counts of subgraphs in a graph is the error in the first step. It has nothing to do with the naive Mild approximation. It has to do with approximation of an indicator by smooth functions. In our context, the passage from the indicator function to a smooth approximation always caused a significant loss. And this significant loss will translate in a highly suboptimal range of sparsity. If you're looking at the problem we mentioned before of Erdos-Renyi random graph, the problem will get more and more challenging the smaller p gets. And because of this transformation to smooth approximation, you will not be able to achieve the optimal smoothness, and you will be stuck with less critical smoothness. These Gibbs measures, however, bring me to the second motivation to this study, which is a collection of things called exponential random graph models. Exponential random graph models consist of, it's a Gibbs measure, it's a special Gibbs measure, where the reference is an Erdos-Renyi graph. What we are doing, we are choosing a graph or edges at random, but then we weight them according to a Hamiltonian, which appear here in the exponent, creating a Gibbs measure, which we are always normalized by 1 over z in order to make sure it's a probability measure. So what is the weight here? The weight here is going to be a combination of counts of various subgraphs in the graph. The simplest case is when L equal 1. I will go over it in a minute in detail, in which case you simply take a parameter beta, like in physics, multiplied by the count of the number of copies of this subgraph H in my random graph G. However, to make it appear on equal footing, especially if you put more than one type of subgraph count, we normalize all of them by the expectation, which will also grow with n, and then we take them through a function, which for a moment you can completely ignore and think of that as linear function. We take the average of these things, if we want to consider more than one, and when we scale it up by e to the r, the factor e to the r is going to fight with the tail of the large deviations of the Erdos-Renyi to make this weight significant enough to change the Gibbs measure, so we don't want the Gibbs measure to look exactly the same as a reference measure. The sign of the value of beta dictate whether we are trying to achieve more appearances of our copies or less appearances. That is like ferromagnetic and anti-ferromagnetic models in statistical physics. And we will be considering throughout the talk only the ferromagnetics, that is, all our parameters beta k will be non-negative, and that will be consistent with trying to look at the upper tail or maximizing the number of subgraph counts. The nhk of G, the count of the number of copies of hk in G, is in such an exponential family as sufficient statistics for finding the parameter beta k. This is well known. If you look at the derivative of the log of the partition function with respect to the parameters betas, you will get the expected value of n under the Gibbs measures and so on and so forth. We are not going
the expectation in the denominator with respect to what measure?
Sorry, the expectation of
in TH is
the expectation is, yes, the expectation is always with respect to the reference measure of the Erdos-Renyi measure. So whenever there is an E here in my talk, it will be with respect to mu and p. And that is because I'm looking at making TH of G is supposed to be 1 under the reference measure. So in the variational problem, it will always be deviations from 1 that will dictate the contribution of the exponential. Thank you for the question.
Thank you.
it is well known that if you have large deviations for the joint upper tail, that is, if you know the probability under Erdos-Renyi, how the log of the probability under Erdos-Renyi behave for the event that the n divided by E of n exceeds its nominal value 1 by an extra constant delta, positive constant delta, if you know the behavior of the rate of this log probability, and if it scales correctly, like 1 over r, or you take r to be the correct scaling, then you can relate the formula, the limiting free energy, the formula for the limit of the log of the partition function, which I called here fh of beta, with the large deviation rate function via a nice variational problem, which is an analog of Legendre-Fenchel transform. What you are doing, you say, look, I can go over all possible choices of my deltas, calculate the probability. The probability of mu is approximately e to the minus r times this function j. This is this formula here telling me. And I multiply it by the contribution I get from e to the rh according to my choice of t exceeding 1 plus delta. So the argument here is 1 plus delta at least. And I plug it here in the formula. Then I take the supermum over all possible values of delta. Delta being equal to 0 correspond to the typical value where I have no large deviation rate function, the rate is 0, and I get the contribution of the typical Hamiltonian. This is well known in large deviation literature. This is called Varatan large deviation lemma. So we have relationship between the tails or the behavior of the partition function of the Gibbs measure and the large deviations for the upper tail probability. And this goes even deeper in the sense, which we will see later on in the talk towards the end, that the structure of typical sample from this exponential random graph models is actually determined by the structure of the Erdos-Renyi, the base measure, the Erdos-Renyi graph, conditional upon the rare event. So if we can understand the conditioning of the Erdos-Renyi graph, given that rare event, that will actually be the typical sample in the Gibbs measure. The Gibbs measure is moving rare to typical. So if you have a problem in application, in science, or in applied probability, which the model is a Gibbs measure, then what was before large deviation is suddenly more interesting because it's a typical behavior. That's our second motivation here. In particular, a simpler model is called the edge H model. Edge H model corresponds to taking L equal 1. It appears a lot in sociology literature, but I will not go over the applications exactly. In this case, we just get a much simpler Hamiltonian. It's e to the beta, our scaling r, times a function of our count of one particular subgraph. And the simplest case will be to take f linear, just x, so you just get the normalized count of the subgraph, multiplied by a constant, then multiplied by a scaling r. And the simpler case will be to take p, the parameter of the Erdos-Renyi fixed, beta, the parameter in the exponent also fixed, and take n very large. In this case, we know that the tail of the large deviation will be scaled by n squared, because that's the number of free edges we have in the random graph, or number of independent variables. So the correct scaling for r will be n squared. And this dense case was studied by Behamidi et al. In 2008, and then in more depth by Chatterjee and Diaconis and Lubetsky and Zhao in 2011, 2012. They were already armed in these two works by the large deviation of Chatterjee and Varadan, so they could get much better results on the behavior of these Gibbs measures through what I explained to you in the earlier slide. There are, however, two deep problems with these models of ERGMs, which you can see even in the model for L equal 1. The first one, we already saw that in the dense case, if beta is positive and p is fixed, in most of the range of the parameters, the Erdos-Renyi, the Gibbs measure, the edge H model, and also the ERGM would look like the green strategy. It will just be an Erdos-Renyi model with a shifted parameter. So there will be nothing interesting in studying this from the point of view of modeling applied stuff. You just get the same stuff you started with no interesting structure. That is one problem from the point of view of the application. You didn't get anything new. From the point of view of the mathematics, it's even worse. You actually have a degeneracy because in some ranges of p and beta, because the number of nh grows as I mentioned, even in the case of triangle, grows like the number of vertices which are having high density to a power bigger than 1, you are in a situation where you are doing an exponential tilting with something which grows more than linearly, in particular grows much faster than the tail of the large deviation rate. So the typical graph in some range of parameter is simply either empty when beta is negative and large enough, or completely full when beta is strictly positive, and the value of p doesn't even affect it in those ranges. So it's really become trivialized. It's dominated by trivial tails. In a paper with Cook, which is underwriting but not yet posted, we are studying the sparse case. We are studying the case where as n goes to infinity, p goes to 0. These are called the sparse exponential random graph models. And those are known to have a richer structure. This was already pointed out in a less specific or explicit way in a paper of Eldon and Gross that looked at the nonlinear, at the naive mean field approximation for the log partition function, but not very accurately, not as accurately as in this paper. And so we actually have an interesting goal, because the goal, we expect to get something which will not look like a Erdos-Renyi random graph in the Gibbs measure. And we also resolve the degeneracy, which I mentioned here, by taking the function f, that's the reason why it appeared here, and it also applies in the more general exponential random graph model, which is raised to some power gamma, and we make the power gamma strictly less than 1. It depends on the number h, on the vector h here, determines the tail, and once you know the tail, there is a maximum level of fractional power that you can take, which will give you the right result. And this was already pointed out in the work of Lubetsky and Zhao that I mentioned earlier in the dense case, and we use this observation and then applied it in the sparse case to get the interesting result. Okay, now we move. This motivates us to go and look at the upper tail for subgraph count. So remind you again, what are we after? We are after minus the log of the probability under Erdos-Renyi of the event in question, which is finding too many copies of H, more copies than typically one would expect. And we would like this upper tail probability to be approximately, that is within little order of 1 relative error, of the scaling R times the nice explicit function J, which depend only on H and delta, in particular not on N and P. And one should choose the correct scale R. And here the correct scale R, if our graph H has maximal degree delta, it will be n squared like before, the number of edges we have. But as the probability P goes to 0, it's important which factor of P we put in front. And the correct factor is P to the delta times log 1 over P. And I will explain later why this is a correct factor. So we put this correct factor, and the goal is to achieve the upper tail probability for this event. And the answer actually is going to correspond to the other two strategies I mentioned. When P goes to 0, it is never going to be the Erdos-Renyi changed mean, the green strategy. But actually, the dominating strategies are the other simple ones, either a planted clique or a planted hub of appropriate sizes, and which one of them is dictated by the choice of H and the parameter delta. And the goal was to prove such a statement, and this was done in a two-stage sequence. First, in the work with Chatterjee, which I mentioned earlier, we found that if P is small, going to 0 with n, but not too fast, that is exceeding n to some small power which depend on our choice of H, then we get the naive mean field approximation for the upper tail by the strategy I mentioned, meaning, what does it mean? It means that this minus log probability is more or less behaving like the minimum of the relative entropy between product measure mu of x and the underlying product measure with a fixed parameter P. And what do? You take the minimum, you look for the closest x, the closest choice of the parameters. X here is a matrix of 0, 1 values. You change the probability at each entry of your random graph, probability of edge from being P to being some number x, ij. And you infimize over all the choices of these parameters. One special case is taking all of them to be Q, that's the green strategy. Some other are like the clique and the hub strategy, where the p's are differing very much, and you take the infimum over what? You don't take the infimum over everyone because that will be 0, but you take the infimum over all the possible strategies where typically the value of the subgraph count will be the number you want. So you just go to tilt by a product measure which satisfies this constraint. And hereafter, I will call by capital phi of n and p the result coming from the naive mean approximation. This is a variational problem, but a rather complicated variational problem because it's a variational problem on the space of all matrices of size n with n choose 2 edges, all n by n matrices. So it's not a single letter answer yet, but this was done in a work of Bashar, Bhattacharya, Ganguly, Lubetsky, and Zhao that followed our paper. They saw, we have a variational problem, and they checked that this variational problem, the optimum to this variational problem normalized by R, is indeed converging to this explicit function JH of delta, which I'm not going to write you, but this explicit function corresponds to what you get if you try either the click or the hub, make the minimal size that will do the job for you, and see which one has the smallest exponent, smallest negative exponent. And this
your TH of X is an expectation.
Right. No, so here TH of X is not exactly expectation. What you do here, X is now a deterministic matrix. So TH of X is really the amount that of counts of subgraph you find where every edge has a weight Xij, and you still normalize it by the same normalization you used for the Erdos-Shreni. So if you put for X, mu, and P, you will get exactly the value 1. A very good question. So THX here is a normalized subgraph count, but it's a deterministic quantity once you choose X. There is no more randomness. We moved from probability to a variational problem. Is the answer clear?
Thank you.
Okay, so what BGLZ showed in 2016 is that this convergence, this mean field, naive mean field variational problem, the large variational problem converged to the explicit variational problem in the whole range from P going already to n to the minus 1 over delta, n to the minus 1 over the degree. So that suggests that this constant here, A of H, which come from my work with Chatterjee, was highly inefficient. And indeed, Eldon, when he improved on the naive mean field approximation strategy, as a test case showed that he can get rid of the factor here and get 1 over the number of edges, up to a constant. But this is far from optimal. The optimal is expected to be 1 over delta. So you should get this first part, this comparing of the upper tail with a naive mean field approximation. You should expect it to be in the same range, as
ci sono alcuni dati che si ricavano dal.
Okay, I didn't hear the question. Okay, I think there wasn't a question. So you expect the naive mean field approximation to work in the same range as a variational problem. So that's our goal here. And indeed, more recently, in 2 papers with Nick, one with Nick alone 3 years ago, and one which was just recently posted with Nick and Pam, on which Nick will talk in the follow-up lecture, we got the constant here to be very close to 1 over delta, first to 1 over 2 delta, and then to 1 over delta plus 1. So we are very close, but this required work which did not go through this smooth approximation, but by a completely different approach, which Nick will explain in detail in the follow-up talk, together with motivation and with implication of this new strategy on other problems in combinatorics and large deviations. In the meanwhile, or at the same time, some work was done for special graphs. If you have a special graph H, then you can utilize a special structure to get nearly optimal result here in this naive mean field comparison. This was done by Ugeri, who looked at cycles and got the optimal 1/2 for L greater or equal to 3. If you look at a cycle, as I mentioned, like the triangle, then you can express the event TH of delta as a trace of your matrix to a suitable power. So you can actually use well-known information or more readily available information on eigenvalues and spectrum of large random matrices to get yourself in a better position, which is a core of Ugeri's paper. In the work with Nick Cook, while we did the general case, we also saw that in a case of a star, where H has one vertex connected to many vertices of degree 1, we can get a much better exponent. And later on, Harel, Muset, and Samotic, and this was taken on and improved by Basak and Basu, which follow the same approach. They use a more combinatorial approach, not going through a probabilistic argument, and analyze the case of a regular graph, where every vertex has exactly the same degree delta, in which case the combinatorics is nicer, the theory of large graphs is more well-developed, and they got the optimal constant, which is 2 over delta. And here, when I write in the results minus or epsilon, it always means that there is some logarithmic correction term. So P is not going to be n to the minus 1 over delta, but some log n to some power. I don't care what it is. Okay, so now that we have the large deviation results for GNP, the Erdos-Renyi random graph, and a single count TH delta, we would like to answer the question, in what sense is it important to take this particular random graph model, and in what sense is it important to take a single subgraph count? Can we take multiple subgraph count, look at joint large deviation? Can we take other graph models? So what is special about the Erdos-Renyi model? What was special was 2 facts. 1, it has complete independence of the edges, and 2, it has complete homogeneity. We have exchangeability. We are using the same P. In a paper with Sohom Bhattacharya, we looked at trying to relax, not completely, keeping the structure, but relaxing these 2 assumptions. And we saw that the conclusions that we drew in the earlier paper with Nick Cook extend to other graph models. For example, you can replace the Erdos-Renyi graph model by a uniform graph, but subject to a hard constraint on the total number of edges. Instead of total number of edges concentrating around n choose 2 times p, you set it to be fixed to a fixed number m. Another slightly more general, slightly more deviating or different classical model of random graph is a random d-regular graph. Here, what you do, you fix a degree of every vertex to be d, which is a typical degree n times p, and you work under this hard constraint. So both of these graphs have a lot of independence because once you condition on the edges, the rest remains independent. But you have some hard constraints here. In the case of the random regular graph, we had to focus on H of a special case in order to do that. And the last family we looked at, again, following Erdos-Renyi, was more also motivated by application, is an inhomogeneous Erdos-Renyi graph where the P is now changing at every edge, like in a stochastic block model, for those who know. So these models appear often in application. We saw that most of the conclusions about the naive mean field approximation, about the large deviation, will extend. What does it mean most? The naive mean field approximation, the first part of the program that I followed with Chatterjee and the one in the paper with Nick Cook, those work very well under changes. But the variational problem, the work that was done follow-up by Bashar Bhattacharya et al., this part has to be redone in each of the 3 cases. And it changes the actual answer JH of delta. And in particular, in a follow-up work of Ben Ganby from 2020, he looked at the case of random deregular graph, where you can actually not do the hub strategy because the hub strategy involved changing the degrees of some vertices to n, which now is not possible because the degrees have to be staying fixed, d. So Ben Ganby showed that for certain special, cleverly chosen h's, the answer is not only changing the j, but even the rate is changes because you are not able to do the kind of tilting that you like to do. But I will not go in this direction. Instead, in the rest of the lecture, what will be more interesting to us is the other type of extension, moving from a single event to a joint large deviation. And this was done in a theorem, which we did first with Bhattacharya under the conditions of Cook and with Cook, and then done again in the new paper with Pham. We also improved the results, the improvement over the results with Nick from 2018 extended to the joint large deviations. What does joint tail means? as I mentioned again, you have a collection of subgraph, more than one, of the same maximal degree delta, and you are looking at P in the range I mentioned, which is much bigger than n to the minus 1 over delta plus 1. And then you have the naive mean field approximation, not for the upper tail of one of them, but joint. What does it mean? It means that the upper tail event for all of the THJX exceeding the specified values 1 plus delta K is going to be equal approximately to the naive mean field, which is a minimum, again, over the same collection of relative of measures, product measures with a varying parameter for every edge, subject not to one constraint, but subject to satisfying multiple constraints at the same time. And already in the paper with Bhattacharya, we have shown that the rate will remain the same, and the problem reduces to a similar rate function as in BGLZ case. The only difference is when you have joint constraints, instead of having either a hub or a click, now maybe the optimal strategy is to have at the same time a piece of a hub and a piece of a click. You might use a mixture strategy, which you do not use when you have only one constraint. So we understand the variational problem, we understand the tails, so we can now look again at the conditional result with the hope of getting to the study of the exponential random graph model. That will be the topic of the next slide.
What is regular two core in the previous theorem?
Let's just ignore the details.
Okay.
It just means that there is a special case of graphs H, which we can analyze, not all of them. Many will not be there. For example, if you take a cycle, it will be a regular degree 2 graph, but you can take a cycle, hang on it some trees on the sides. 2 core means a subset of vertices, the degree of each is at least 2. So if you hang a tree on a tree will disappear because in a tree there are leaves of degree 1, you will eliminate them and keep eliminating the whole tree, and then what will be left is a cycle in the center. So you can look at a family of graphs, but not all of them, and the reason is, as Ben Ganby pointed out, is that for some graph, once you go to the regular case, the degree, the rate itself changes, but I'm not going to go in this direction. So again, we are looking at the typical structure of the upper tail event, as in the second slide of the talk, but now for sparse random graphs. So I remind you what the situation is. We have a fixed subgraph to count, triangle or something more complicated, of maximum degree delta. We calculate the number of copies in our random graph, Erdos-Renyi, divided by its expectation, so it's concentrated around 1. We are looking at the set of graphs whose value exceed by a fixed amount delta the typical value. And we want to study the graph conditioned on this rare event. How is the graph look when it is conditioned on this rare event? Based on what we know from the variational problem, we will expect, at least in the domain of validity of the work of BGLZ 16, that conditional behavior will look like the original GNP graph, meaning Erdos-Renyi, except for planting either a click or a hub according to the one that seems to match the result for the tail probability. And which one you do, determined by the value of this function JH of delta. So determined only by H of delta, it's a simple calculation to find. It's explicit, but I don't want to write all the formulas. So that is the goal of the conjecture. And you can see it kind of in this slide. This slide represents the three type of behavior of the conditioning that we can see, the simple ones. You start with a matrix. This is a adjacency matrix for our random graph A. This matrix if you look from far away and you think of ones as black and 0 as white, the average grayness will look like P, because on the average you have a density P of ones in your graph. And the tilting or the conditional behavior, the simpler one was the one we saw for the complete graph, simply slightly darker gray. Everything looks like an Erdos-Renyi. The other ones, the click and the hub, look like keeping the grayness more or less the same, but there is a small piece which becomes completely black. This corresponds to a collection of vertices which are all having edges between them. This is a clique, the blue, and the hub, the red, where you have a smaller collection which is connected to everyone else, counting on some edges coming from the P to complete the picture and create the excess of number of copies. Now, in this picture, there are typos because it was done for an earlier version of the talk where capital little n was capital N. And another thing was it was done for the case of triangles where delta is equal to 2. In general, the P square should be P to the delta, and the P should be P to the delta over 2. Now, what determines the size and also what determines the scale? I want to remind you the scale of the large deviation was, I remind you, n squared P to the delta log 1 over P. Where is it coming from? Just count the area of the ones, okay? Suppose we have ones of size Rj, of size, let me look at the size of the ones. Here, I choose n P to the delta over 2 times n P to the delta over 2. So the total number of ones I have is of order n squared P to the delta. The probability of choosing ones here where there were supposed to be P's is going to be P to the area of the black. So if the area of the black is n P to the delta, like here or here, n times n P to the delta times a factor j, what we will get as a change of measure to make all these edges 1, we'll get P to this power. And P to this power is exactly e to the minus j times r if you choose this choice of r. So that's really where the scaling of the rate comes from. And the rate functions, the coefficient j, is really going to be simply the amount, the area of black you need in order to achieve this change in the number of subgraphs, which you can calculate. So that's really the principle. The black dominates the changes in these sparse graphs. So we want to verify this conjecture again. And I showed you the picture, and this was done first in the special case of complete graphs, like triangles. So if you have a complete graph over delta plus 1 edges, this is a special case of a regular graph. It's a very special case with lots of symmetries. In this case, Harel et al., when they calculated the tail of the large deviation, managed also in the optimal range to show what I just mentioned, that conditional on the rare event, conditional on this, a graph indeed will contain almost a clique, almost this black picture, and almost a hub of the correct area, which I mentioned before, j times n squared times delta, p to the delta. So this is a result which is slightly weaker than the conjecture because they cannot establish the fact that the density in the gray remains, that the gray part here remain unchanged. What they can show is that you must have the collection, the planting stuff, but not the other one. In the paper with Cook, which is under writing or will be posted soon, we managed to do the same result, the same conclusion, in a range slightly weaker. The range is coming from our work with UE, PAM, but we can manage to do it for any age, not just regular. Any subgraph that you want to count, we can do the same. And we can even get a stronger statement which matches this above conjecture if you take a slightly weaker range which correspond to the work, the earlier work with Cook. And the reason for this difference is because when we go from the work with this in the smaller range to the work in the larger range, it cost us in moving to a way or covering or a way of measuring distances which is more relaxed. And therefore, in the conditioning, we cannot get the same stronger conclusions than we can get in the narrower range. And here, 2 delta stars, the coefficient which appears here is simply you choose every edge of the graph H, and you just sum the degrees on both ends of the edge. So the degrees on both ends of the edge, if you take one vertex to be the one with the large maximal degree delta, you will get at least delta plus 1, which is a number here. It's a delta for one and at least 1 for the edge for the other one. But there are many graphs, for example, regular graphs, where you will get delta plus delta. So you can go at most 2 delta and at least delta plus 1. So that's this other range. Okay, equipped with this, let's look at the typical sparse exponential random graph model sample. So we are looking at, we fix a collection of vertices of subgraphs H, which is going to be the one we will use in our variational problem. And we fix two vectors, delta and beta. These are the vectors of the parameters for the tail of the Erdo Shreni, and these are the parameters for the parameters beta in the exponential random graph models. Both of them are positive. Then there is a simple calculation of the variational problem in JH of delta, which I never wrote to you, but you can check that the set of optimizer of this variational problem must be finite. It may be single, which is even better, but it must be finite. Under some extra conditions that you need to write, you will also have a finite set of optimizer for the associated variational problem I showed you earlier for FH of beta. Example, in the edge triangle model, this will be the case, that you have a finite set of optimizers. So we assume hereafter that both sets of optimizers are finite. Under this condition, in this paper with Nick that I mentioned, and in the process of writing, we have the following result, which is a formal way of expressing what I wrote in the earlier slide, which means the following. You take P in the range I mentioned, you take a fixed epsilon, then you look at the Erdo Shreni random graph model conditioned on the rare event. So a sample from the graph conditioned on the rare event with high probability, with high conditional probability, will have this following structure. You choose one of these optimizers, if there are more than one. These are the parameters, if you want, of the size of the clique and the size of the hub you are going to use to get the rare event. You choose two disjoint sets, I and J, of the right sizes. I is the size of your almost clique, and J is the size of your almost hub. They are of the right sizes, P to the delta n and square root P to the delta n, with coefficients A and B, which dictate how you divide between clique and hub. And then you should get an almost clique and an almost hub. What does an almost clique mean? Almost clique means that if you would look only at the degree of the subgraph where you remove everybody except the vertices in I, you get almost the optimal degree. They may not have complete clique, but you get at least 1 minus epsilon, epsilon being a very small tolerance parameter of the possible edges. And in the hub case, the same. If you look at the vertices at the hub, at least almost all of them will have a degree which is almost n, not n, but exceeding 1 minus epsilon. And again, epsilon being a tolerance parameter. So this fact is exactly what I mentioned by having the graph containing almost the optimal clique and almost the optimal hub. In the narrower range, we get in addition the following result. We get in addition that our adjacency matrix is closed in a spectral norm to a deterministic matrix X, which characterizes a clique and hub situation. And deterministic matrix X will be of, again, the same choice of I and J as before and A and B as before. And it will be a matrix which has P everywhere, except when the two edges are at I, or one in J and one not in J. That's exactly the dark area which I indicated in the clique and in the hub. So you have a deterministic matrix X, and your adjacency matrix will be very close to it in spectral norm. That means that not only are the black size going to match, like in the red and blue here, but also the rest of the graph will be very close to P, meaning will be Erdo Shreni graph. Now, if you change A and B in this story, these parameters A and B, from the set of optimizer for the J to the set of optimizer for the free energy, you get exactly the same conclusion, but now with high probability for a typical sample from your exponential random graph. So what was conditional here, there is no more conditioning, it becomes a typical. So this really explains the structure I was aiming at in the beginning of the talk. And in the remaining...
Spectral norm is Hilbert-Schmidt, or what is spectral norm?
Spectral norm here is the maximum of the quadratic form, or if you want the maximum, these are symmetric matrices. It's the size of the largest eigenvalue in absolute value.
Thank you.
The proof here, I will not go over the proof, but it crucially used stability results for the relevant variational problem. That's really what you need to do, because in all the analysis, typically what you do, you get for free the lower bound by simply checking the winning strategy. You check some way to do things, and you see that you get at least a certain probability conditional, or at least a certain contribution to the exponential random graph. And then you work hard to show that doing everything you can is giving you a matching upper bound. But what you need in order to get the conditional result is to actually show that whenever you deviate from the winning strategy, you exceed the exponential, that you do not lose some other strategy, which is neither blue nor red, but something more complicated, which may match them. So you need to actually look at the variational problem and study stability results of it. So that's kind of a lot of analysis, which I'm not going to go through. Let me, in the remaining 2 minutes, try to give you a very quick survey of what Chatterjee and Varadhan did, preparing for the talk of Nick, which will repeat it, but also going more into the sparse case, which is more challenging. So this is kind of a quick overview of large deviation theory. If you have a set of probability measure on a common topological space, large deviation principle is asymptotics of the form minus log of the probability up to a scaling is given by a solution of a variational problem where you take the minimum over all the possible entries in the set you care about in your space X of the certain rate function J. In the dense case, Chatterjee and Varadhan prove a large deviation principle for the Erdos-Renyi graph. But what exactly does it mean? After all, the Erdos-Renyi graph live on different spaces. We are working on Gn, and as we change n, the space changes. So what we need to put them all in a complete topological space, in the same space. And the way to do it is by the theory that was developed in combinatorics called the theory of graphones. A graphone is like a graph, but you change the discrete to a continuous. So a graphone is a function from 0, 1 squared to 0, 1, which is symmetric, has nice measurability properties, and it is equipped with a topology coming from something called the cut norm. The cut norm of a function is going to be to integrate this function over all possible boxes, and then you take the absolute value and take the supremum over the box. Notice importance, the absolute value come after you integrate and not inside. It's much weaker than the L1 norm, because the L1 norm, you cannot do large deviation under L1 norm for subgraph counts. So that is called the cut norm, which is suitable for this purpose, as we will see in a minute. Graphones are really limits of rescaled adjacency matrix, where the cut norm extends the matrix cut norm. The matrix cut norm is exactly the same, but now you have a finite matrix, Mij. So you choose two collection of vertices, or sub collection of rows and collection of columns, and you take the maximum over all rows and columns of the absolute value of the sum of all the entries in these rows and columns intersection. That's a matrix cut norm. And what is the connection between graphs and graphones? It is in this picture which I showed you earlier. Remember this picture? You write a very large adjacency matrix of a finite graph as a matrix, and you think of making this into the unit box. So the entry ij or xy will be sitting in nx times ny. And you look at the adjacency matrix at nx, ny, where x and y will be now real from 0, 1, you will go over all aij. So the top corner here will be a little box of size 1 over n over 1 over n. And this will be like a piecewise constant graphone. And a general graphone is just a continuum of this. You make the graph very large, the picture gets blurry, like looking at a picture in a museum from far away. And these are our strategies, look like these typical choices of graphones. Now, the graphone space provides for us a topological reformulation of the classical regularity method from extremal graph theory. And there are two results in combinatorics which have analogs in graphone theory. And these two results are first, that the space of graphones with a cut norm topology is compact. That's very useful for large deviation. This is Semeradi regularity lemma. And using this, Chatterjee and Varadhan get themselves the large deviations I mentioned to you. The compactness is crucial here in order to be able to do large deviations. And the second fact, which is relevant to our story, is that counting subgraphs suitably extended to our space of graphones from graphs is going to be continuous with respect to this particular norm we choose. This is called the counting lemma. Now, because it's a continuous functional, once you have the large deviation as a corollary, you can get the upper tail for our count. So that's where Chatterjee and Varadan got in 2011 with the result I mentioned. So the moral of this story is that the cut norm topology is perfect for subgraph counts in dense graphs. However, it is very poor for subgraph counts in sparse graph. And the reason for that, both the regularity lemma and the counting lemma from extreme combinatorics are not accurate enough to analyze sparse graphs. The problem, sparse graphs, P goes to 0, so you are very close to the 0 graph. You're actually all sitting in the cut norm topology in a tiny ball. Everything you do is also in this tiny ball. So you cannot see anything with this approach. And actually, it is known that the regularity and counting lemma from extreme combinatorics are already sharp. So it's not like you will improve them, you will get anywhere. And if you want to hear the solution, you need to attend Nick's talk. He will talk about this and many other ideas. Thank you very much.
Thanks a lot, Amir, for this beautiful talk. Are there questions or comments? Please write either to the chat or unmute yourself.
I understand there is some alternative or typical graph with condition looks like G and Q, with Q differ from P, or it does look like initial G and P with included clicks or hubs. Huh? It is sense of your theorem or not?
Right, right. You can also get a click and a hub together, a mixture of the two, and it depends on when P is fixed. In most of the domain, you get the simple strategy, the green one, or G and Q. In the sparse case, you typically will get a click or hub or a mixture of click and hub, and you will not get anything else except in the area which is question mark, where you will get something much more complicated, but we don't know what. And also, everything I said is in the ferromagnetic regime, where you try to look at the upper tail. You are looking for graphs with a large number of subgraphs subject to a given number of edges. If you are trying to reduce the number of subgraphs, it's a completely different story. You get into much more difficult extremal combinatorics. These are become anti-ferromagnetic model. You're trying to essentially kill the number of edges. You're looking for making less edges in order to make less structures, and the story is very different and much less known. The story here is very clear. Now, the story in the other domain is not known at all, or very little is known.
Thank you.
Very good. I don't see further questions. Let's unmute ourselves to give Amir an applause. And we have a 3-minute break, and we'll then continue with Nick's talk. So Nick, maybe you try to share already.
Nina, did I unshare just to make sure that Nick can share?
Yeah, you did unshare. Nick, you are co-host and should be allowed to share.
Okay. Okay, you can see this?
Yeah, works well. Let's wait again 2 minutes.
Okay.
Nick, your voice is not clear, Nick.
Okay, how is it for you, Nina?
Say something.
Something.
Yeah,
Is it,
for me it's
That's
okay.
okay.
Amir, is it not good?
It's okay. It's possible, but you might have a weak connection. I don't know.
okay. Yeah, I'm not sure what to do about that at this point. I know the mic I'm using is better than the internal mic. Right. Well,
Connect your. If you can connect by wire, it's
is this? Do I sound quieter now, or how does it compare? Can you hear me now?
I hear you, but not loud. But
Okay. Yeah, I was just trying the internal mic, but it's. I think I'm much too quiet, so I'll stick with this. Okay, but yeah, just let me know if I become incomprehensible.
okay, very good. Let's reconvene. So the next speaker in this session is Nick Cook, and he will talk about large deviations and the regularity method for Erdős-Rényi hypergraphs. Nick?
Okay. All right. Thank you. So thanks, Nina, for the invitation. So this is a continuing on a lot of the material that that was in Amir's talk. Mathematically it'll be self-contained. I'll just it'll be lacking a lot of some of the applications and motivation. But I'll be going a bit more into the math.
Nick, you have to speak up. You're quite not
Okay.
loud enough, I think.
Okay. Let me just move it closer to me. Is this a bit better now?
Yes.
A bit better. Okay. Okay, thanks. Okay, so as I was saying, I'll be going a bit more into the math. It'll be mathematically self-contained, and not talking about some of the motivating material. So you can see Amir's talk on YouTube for some of the applications. Okay, so just starting as Amir began. So in general, to sort of beginning from the vantage point of extremal combinatorics, there's a general problem of you have two functions on a finite set. So for us, this finite set will be the set of all graphs on n vertices with n large. And then you can think about two different functions. And you want to understand the behavior of one under a constraint on the other. So here I put it back partly because I want, since I'll be going a bit more into the math, I want to switch notation a bit. So Amir was talking about counting subgraphs. It's convenient for us to count subgraphs in the sense of counting homomorphisms. So graph homomorphism is we're just mapping the vertices of our fixed graph. So think of it, H is always a small fixed graph, like a triangle. You're counting the number of different ways of mapping this fixed graph into the big vertex set so that every edge of the fixed graph, so say every edge of the triangle, goes to an edge of the big graph. So this is the sense in which we're counting subgraphs. This gets some repetitions because you do overcounting depending on the order of the mapping, and then there's also some degenerate copies you might get if you reuse edges. But the differences aren't a big deal, at least in the regime of sparsity we're looking at. Okay, so and then we're thinking, so I'll write hom for the number of graph homomorphisms, and so you can think about these two functions, counting the number of triangles and the number of edges. So the complete graph on 3 vertices is a triangle, and on 2 vertices is just a single edge. Okay. Okay, so this is the main motivating example. And then, as Amir mentioned, you have the extremal problem, which is you can think of trying to maximize the number of triangles under an upper bound constraint on the number of edges. And here, so this is at least in the case of triangles, you can get this very easily in a lot of ways. So there's a general bound having to do with simplicial complexes. The Garciatoma theorem says that gives you this upper bound on the number of triangle embeddings. So this will be upper bounded by L to the 3/2, where if you constrain the number of edges or edge embeddings to be at most L, then you have this upper bound L to the 3/2. And you get equality here for the case of a complete graph. Okay, and so this is for triangles, but these sorts of bounds have been established. So sharp bounds of this type have been established for homomorphisms of general graphs and even general hypergraphs. So this was actually the subject of Nogar Alon's very first paper. And then the hypergraph setting was studied by Friedrich and Kahn. And you can also get these, it's been realized that you can get these as a consequence of a certain generalization of Hölder's inequality, which is Finner's inequality. Okay, but so this is all this deterministic problem. I want to mention these things because they're sort of in the guts of the proofs for these large deviations results. Okay, and then so we have the extremal problem. You can also study the typical behavior, and so Amir also mentioned this, but you
Да, я сделала, но у меня просто...
So you can study, say, take a model of a random graph where, so you're not putting you don't think of this as an upper bound constraint, but say you pin the value of G, say the number of edges to some value, or you take a model of graph where at least an expectation, it tends to be that value. And then you study what's the typical size of the more complicated function, which is, say, the number of triangles. Okay, and so you can easily compute the expectations, and then you can also prove the law of large numbers, and the central limit theorem was even obtained by Adjacency. Okay, so and in between these two regimes, we have the large deviations regimes, and there's two sorts of problems that Amir was talking about. One is to understand, so to get precise asymptotics for the tail, so you have a probability of deviating to something below what you have from the extremal bounds, but away from the typical. And then a more refined type of question is to understand sort of what does your structure look like when you condition on this tail event. And studying this problem, it's related to studying the stability of optimizers for the extremal problem. So I mentioned that, say, if you're maximizing the number of triangle embeddings, then you can do this with a clique. And so then a natural question is, if you want to come very close to the maximum, are you necessarily very close to a clique? And the answer is yes. And there are recent works on stability of these deterministic bounds that I mentioned on the previous slide. So Loomis-Whitney inequality is a special case of this Finner inequality. Okay, and just to mention in passing, so our talks are focused on upper tail problems. There's a lot of interesting work on corresponding lower tail problems. So there's extremal lower tail problems. So say for triangles, so for triangles you can so you can study the number of triangles. So if you fix the number of edges, how few triangles can you have? So the extremal problem was solved by Razbarov using this flag algebras technology, and then there's also been work on the large deviations problem up to just very recently, a nice work of Kosma and Samotic for the sparse case, but I won't say anything about this. Okay, so these this in-between regime, these large deviations problems, they're interesting because to some extent they inherit some structure from the extremal problem, So for instance, as Amir discussed, one mechanism for creating lots of extra triangles, say, is to deviate from a sort of typical looking Erdős-Rényi graph, which will have an adjacency matrix or graphon looking like this, to something that looks like this, where you plant a clique. And this construction, you can see, this is just inherited from or suggested by the extremal problem. As you can just, we know from the best way of in the extremal problem, the best, if you really just want to maximize cliques, maximize triangles, you put all of the edges in a clique. And here it's the answer is, okay, well, we can do something like that. We can take sort of the excess edges and pack them all into a clique. So we get all of our extra triangles by sort of planting a small version of the extremal problem. So this just sort of ignores the rest of the graph. But you get some new phenomena as well. So for instance, there's this hub phenomenon that that sort of combines some of the planted structure with some of the typical edges that are available. And so one thing we've learned that through a lot of these works that Amir mentioned is that it's, in the sparse case, it's just sort of a choice between these two. But when you go to other models like the regular graphs, or to think about joint upper tails, then you get much more complicated looking structures. And also there's been recent work on the hypergraph setting that I'll talk about, where the picture is also much more complicated and still not very well understood. Okay, so in this talk, I want to sort of motivate this study of large deviations from a quantitative perspective that you can think of as sort of trying to understand the geometry of the space of graphs, seen as sort of being embedded in R, choose R to the n choose 2. So you can view it as a subset of matrices and study this as sort of a subset of a norm space. And under various norms, you can learn things about the structure of these graphs and the geometry of the space and of level sets of functions you're interested in. Okay, so all right, so large deviations principles are sort of giving you a handle of the geometry of a space. It's the sort of correct level of generality for framing a large deviation principle, as was done by Varadhan, is in the setting of a topological measure space. And so the classical large deviation principle gives a description of sort of the landscape of your topological measure space with respect to a sequence of probability measures. So it tells you, it sort of refines a law of large numbers by telling you where these concentrate, but then it also tells you at an exponential scale sort of the relative likelihood of regions away from this region of concentration. And it does this in terms of a rate function. So a lot of this information on the geometry is contained in the rate function. And then when you have a large deviations principle, you can get a lot of things from this. So in this very general form, you can then apply it to any sort of continuous function you're interested in. You could get, say, asymptotics for probabilities of events that look like this. Just for instance, you might have two functions, and you want to understand this sort of intersection of super level sets. And the large deviation principle reduces this to an optimization problem. Also, so you might not just be interested in tails, but you might be interested in Gibbs measures, and you can apply the large deviation principle through what's known as Varadhan's lemma to get asymptotics for the partition function of the Gibbs measure. Okay. So the results that Amir talked about for upper tails, upper tail asymptotics are of this form. They are, in some sense, a large deviation principle, It's just your topological space is the real line, and the sequence of measures is the sequence of distributions of the random variable you're interested in. But the real power of a large deviations principle is when you have it on a higher dimensional structure, and then you get it for all sorts of functions by sort of projections or contractions. This, as Amir mentioned at the end of his talk, this doesn't fit the classical framework in our problem about graphs. So for our problem, it doesn't fit this framework because our underlying spaces are changing with n. So it's not just a sequence of measures, but it's a sequence of measures on a sequence of spaces. And so in the dense case, there's a nice way to still get a large deviations principle, which is to go to the space of Graphones, which sort of provides a completion for the space of all graphs of all sizes. And so it was in this setting, so I won't redefine Graphones and I won't use Graphones in this talk, but it was in this setting that Chatterjee and Varadhan proved a large deviation principle. So they got a large deviation principle for the sequence of Erdős-Renyi measures when P is fixed on this infinite dimensional space of Graphones. Okay, and I also won't write what the rate function was. Okay, so that's an LDP in the classical sense of an LDP. So what's nice about Graphones is they give a topological reformulation of these facts from the regularity method. So in extremal graph theory, there's what's known as Semirates regularity lemma, and in the language of Graphones, this says that this sort of infinite dimensional space is a compact space. And then the other useful fact for these upper tail problems is that these functionals that we're interested in, these homomorphism counts or subgraph counts, say, they extend as continuous to continuous functionals on Graphones. And so the LDP that they got, which crucially used the regularity lemma, the compactness. When you combine this with the counting lemma, then you can get upper tails for all of any homomorphism count or joint upper tails, reducing it to a sort of an optimization problem for the rate function. And that's because these functions are continuous. So when they're continuous, that means their level sets will be in your topology. Okay, and so and then this you get then an optimization problem for the rate function, and then there were some other works that analyzed this. Okay, so now we're interested in sparse graphs, and the problem with sparse graphs. So when P, the parameter for the Erdős-Renyi measure, is going to 0, then the Graphon space doesn't provide an informative large deviation principle. So you know, for instance, it will tell you that your sequence of graphs is basically just the empty graph. So it's converging to the empty graph, and it doesn't give you finer information than this. You might think that you could sort of rescale things appropriately so that things don't go away in the limit, but that's actually not possible either, because of what we call a localization phenomenon. So these constructions of planting a small clique or a small hub, these are mechanisms for large deviations that come from a vanishing proportion of edges. So this cut metric isn't going to be able to see them. And what's worse is that those structures happen at different scales. So you can't sort of pick one scale to look at. So the hub was on far fewer vertices than the clique. So it looks like, and it's true, that you can't study these functions on sparse graphs in terms, on a common topological space. You're just not able to situate everything in a common topological space with a single norm. Okay, but you can still say things. you can sort of go into large deviations theory and just extract sort of its quantitative essence. So what the Chatterjee-Varadhan LDP is really doing is breaking our space of graphs, so which you can think of as the hypercube of dimension n choose 2 for the number of edges, breaking this into neighborhoods of a bounded number of graphones. So this is the regularity lemma, is a sort of compactness fact that you can sort of cover your space by neighborhoods of a small number of graphones, and these are neighborhoods in the cut norm. And so then you're just asking, so say you're interested in estimating the probability of some set in your topology, and so you're basically just covering it by small balls, and then you have to understand the probability assigned to each ball. Well, this part can easily be made quantitative. If you go, we framed everything. So in general, large deviation principles make sense on a topological measure space. If you give it a bit more structure, if you work in a topological vector space, then you have a nice non-asymptotic upper bound. So this you have this sort of upper large deviations principle with no error term, and it's non-asymptotic for convex sets. So if you have a convex set, then you get this large deviations upper bound. And this is just an easy exercise. It's actually an exercise in Amir's book using the minimax theorem. Okay, and it's with an appropriate j coming from u. It's the convex dual of the log moment generating function. But okay, so I won't make any of that explicit. Okay, so all right, so we can do quantitative coverings perhaps. So we can try and cover events by small convex sets. And then we're interested in these functions, these homomorphism counts. And we will be successful with this covering approach if we can show that, if we can find a family of convex sets where these functions we're interested in don't vary very much on these small sets. So here, what I'm doing now is, so these are the homomorphism counting functions, but I've extended it. So before we were working on the discrete hypercube, and then it was just counting and homomorphisms. Here we're now on the solid cube, and so I multiply weights. So it's not just zeros and ones, but I've got weights. So here this is sort of a weighted count of mappings from the vertices of the small graph to the vertices of the big graph. And then rather than take the indicators that, an edge from H went to an edge in G, you multiply the weights together. So now this is a polynomial that extends in a natural way to the solid cube. Okay, and this is a topological vector space, of course, or it's a convex set in a topological vector space. So this is basically the summary of just the basic approach is what we're extracting from classic LDPs and from the Chatterjee-Varadhan approach is well, we'll do compactness and counting lemmas too. We can just do them in a quantitative way. So estimating sort of metric entropy and covering numbers really is just a way of quantifying the compactness of a set. And then we'll be controlling the variation of these functions we're interested in. We need quantitative sort of Lipschitz constants for these under appropriate norms. So that's sort of getting quantitative counting lemmas. Okay, so with Amir, we implemented this approach for the case of graphs. And the norms we used was the spectral norm. So the spectral operator norm, recall, here is, so this is, you can, this is the supremum over testing your matrix on the left and the right against the unit vector in L2. We only apply this to symmetric matrices, so you could take the same vector U here. And so in this setting, we get a covering by spectral norm balls, which is sort of playing the role of a regularity lemma. So this is sort of a simplified statement of what's effectively a quantitative spectral regularity lemma. And so what it says is, okay, so here we have this sort of constraint. This is in some sense, this is the optimal constraint on P that Amir was mentioning in his talk in terms of, this is the range of P where you'll either have a clique or a hub construction for upper tails of triangles, say. So if you assume P doesn't shrink too fast, so we have this constraint, then for any small parameter epsilon and large parameter k, we can cover our solid cube of weighted adjacency matrices with a collection of, okay, so this is a typo here, so it's exponential to the little o of n squared p to the delta log 1 over p balls. Okay, so the key here is that this is the large deviation speed, and so we want the number of balls to be negligible in compared to this rate, in comparison with this rate. And then the balls need to be of the right size, and so they're balls of this radius, epsilon n p to the delta over 2. And this turns out to be just right, because if you look at these clique and hub constructions, so say planting a clique of the appropriate size, planting a clique, you can use a rank 1 perturbation of the matrix. In that matrix, that perturbation has spectral norm of order np to the delta over 2. And similarly, the hub construction is it's a rank 2 perturbation, but it also has a norm of this size. And so you want your balls to be small in comparison to this. If you're going to capture the sorts of localization, then spectral sort of root needs to be, say, a factor epsilon over the size of the things that you want to pick up. Okay. Okay. Now, and all of this is outside an exceptional set. So, Amir mentioned the regularity lemma, which can be, so there is a spectral proof of the regularity lemma. The regularity lemma is optimal in some sense. There are some graphs that you really need. So it turns out that you really do need some graphones with extremely complex structure in order to approximate things in general. If you allow yourself to delete a set of tiny measure, then you get sort of the approximation and the covering that we're interested in. And the key here is, you just delete a set of probability going zero. It has to be smaller than your large deviation rate. So that's why k is a parameter that you can take something that's negligible, sort of an covering that's able to detect all the phenomena that are interesting. Okay, to go with this, we have counting lemma that basically says homomorphism counters under the spectrum. So here we have a parameter epsilon and a large parameter L. And if we have any convex set of weighted adjacency matrices that has diameter small compared to, okay, so here nice delta, but then we have something called delta star, which is the average of the max degree of
Nick, what happened? You stopped sharing. Nick, do you hear me? I think we have to wait a few minutes such that he can reconnect. Yeah, I think connection was suddenly gone. So let's just wait until he reconnects. I will go to my email and see if he writes a message.
Hello?
Yes, Nick?
Okay. Yeah, I'm sorry about that. My computer.
I think you lost connection. Are you back?
Yeah, no, my computer just died.
I see.
I don't know why. Okay, so let me just share again. Sorry about this.
Yes, let me again maybe make you co-host.
Oh yeah, yeah.
Now you should be allowed to share.
Okay, can you see this? You can see this now? My
Yes.
slides? Okay.
But you have to enlarge to go full screen somehow. Okay.
Right. Try that again. Okay, how is this? Can you see this? You can see this okay?
Yes.
Yes.
Okay.
But you have to speak up again.
Right, okay. I'm just connecting these. Okay, I've got the other mic connected. Okay, all right, very sorry for that delay. Okay, so all right, so I was just finishing discussing this spectral regularity lemma and counting lemma of sorts. So these are quantitative versions of regularity and counting lemmas. The regularity lemma sort of gives you the right.
You got this, Nick. You got disconnected at the end of the spectral regularity lemma.
Right. So you're seeing slide 7 now.
Yeah, but you did not discuss the spectral counting lemma, or at least nobody heard you discuss it.
Okay. All right. So right. So our spectral counting lemma. So this shows you that the homomorphism counts for weighted graphs are continuous in the spectral norm. It doesn't give you continuity in the so can you see my cursor now? Can you see my cursor?
Yeah.
Okay.
Yes.
All right. Yeah, I'm not using the iPad anymore. Okay, so it doesn't give you the optimal sparsity range, but it says that that they're continuous on balls of appropriate size. So here now I use, so this is similar notation to Amir, where I use this normalization of the homomorphism count. So I normalize by the expected size, so that we'll be interested in showing that it's sort of small, that the difference is small compared to 1. So these are typically of size 1, and we want to get it that it's sort of big O of epsilon. And this we can do. So we can show that these functions don't vary much on sets of a small diameter, provided that you have some control on, provided that the homomorphism counts of all subgraphs it is not too large. So they can be sort of, you can set a large parameter L, and then if you're on a set where all of the subgraphs, at least somewhere in your set, have homomorphism counts that are at most this level, then you get this nice Lipschitz behavior. Okay, so in general, you know, if you don't make that, if you don't impose that condition, then these can be behaved much worse. Okay. All right, so now I want to talk about the more recent work, so where we look at hypergraphs, but we also, so in order to study hypergraphs, of course, hypergraphs don't have a spectrum, so we need to get away from the spectral norm. And so we go back to something that's more closely related to the cut norm. So we develop some generalizations of the cut norm. And I first just want to explain these in the simple setting of matrices and graphs, because they're sort of doing a few things. I mean, there's aspects of these norms that are helping you study hypergraphs, but then there's other features that are nice in terms of detecting these localization phenomena. And so, you know, I want to explain them one at a time. So let's first think about localization and how to detect those with these norms, and then at the end we'll take a peek at hypergraphs. Okay, so first, just to recall the cut norm. So we'll be considering modifications of the cut norm. So the cut norm, say the cut norm difference between two matrices, you can think of in a way that sort of looks like the spectral norm, where rather than testing against rank 1 matrices, where the factors have unit L2 norm, you're testing against rank 1 matrices, which are just 0, 1 so-called cut matrices. So these are just this is just the outer product of two vectors that are the indicators of vertex sets. Okay. So that this is just rewriting this. So this is, in terms of graph adjacency matrices, this is counting the number of edges going between U and B. And you can think of this as testing the matrix against a so-called cut matrix, which is just the indicator of a box. And then, okay, so here we have the classic counting lemma, which just says that the homomorphism count, this is a Lipschitz function in the cut norm, and the Lipschitz constant is the number of edges. And this is fine, this would be fine for us. In some regimes, I mean, this, you know, since H is fixed, we don't care about losing factors like that. Okay, so okay, so I just want to give a picture of the proof, to just give you an impression of the proof, to motivate, because this is really where the idea for these new norms come from. So one way you can prove this is, well, so you can think of A and B, so these are adjacency matrices, and you can think of them as being adjacency matrices for you have two different edge sets on a common vertex set. And so let's say the edges of A are pink and the edges of blue are of B are blue. And say we're looking at counting triangles. And so what we're trying to estimate is the difference in the number of pink triangles and the number of blue triangles. And we want to control this in terms of the cut norm difference between A and B. And so what you do is you can write this difference as a telescoping sum over the number of edges. So that's where this factor is coming from here, is it's coming from doing a telescoping sum, where in between you're counting differences between sort of multicolored triangle counts. So say you can count, you have here the number of pink triangles, the difference between the number of pink triangles and the number of triangles with 2 pink edges and 1 blue edge. Okay, so you telescope it as these 3 types of sums. And then you want to control each of them in terms of the cut norm. And so I'll just look at this first one here. So the difference between the number of all pink triangles versus triangles with 2 pink edges and 1 blue edge. In terms of the adjacency matrix, that looks like this. So I sum over the 3 different possibilities for embedding the vertices, the 3 vertices. And then I want ij and jk to be pink. So the edge ij, the edge jk to be pink. And then I'm looking at the difference between, so for the edge from I to k, I want to look at the difference between having it be pink versus having it be blue. Okay, well here, what you can recognize is, so if we can rewrite this sum as first sum over I and k. And so this is just, you can think of it as first embed the 2 endpoints of the edge where you're counting the difference in color, and then sum over the rest. In the case of triangles, that's just summing over a single vertex. But the key point here, and this carries to general H, is that this summing over the rest is a cut matrix. So what you do is you're looking at the difference between the edge at edge ik, whether you have pink versus blue, and then having embedded, chosen location I for one endpoint and k for the other, then you just have this count of all the rest, all the possible embeddings with those 2 endpoints fixed, and that's a cut matrix. So you can see that this is the outer product of 2 Bernoulli vectors. So you can express this as the difference of A and B, inner product with a cut matrix T. Okay, so we'll later generalize these to what we call test tensors, and so that's why I use T. Okay, and so since this is a cut matrix, it's controlled by the cut norm, and that's the proof. Okay, so that sort of will motivate some of the decisions we make in terms of how we adjust the cut norm for our purposes. Then there's how we'll adjust the regularity lemma. So to motivate that, let me recall the Fries-Kanon regularity lemma. So this is the so-called weak regularity lemma. And one way of saying this is that is in terms of a decomposition type statement. So it says that any matrix with bounded entries, you can decompose it into 2 pieces. There's a structured piece that will be a sum of a small number of cut matrices, and then a sort of pseudo-random piece. And it's pseudo-random in the sense that its cut norm is small. Okay. Is there a question? Okay, so the Fries-Kanon weak regularity lemma says that you can decompose any matrix with bounded entries into a sum of a structured piece that is a sum of not too many cut matrices, and then a remainder that's small in the cut norm. Okay, I'll skip okay, you can ignore the proof of that. But the basic idea is just to iteratively take cut matrices. If you haven't achieved the approximation within epsilon that you want, that means that there is a cut matrix where you get a big difference when you test against this cut matrix, and then you just add it to your collection, and you just keep adding them until you've got a good enough approximation. And just basically by Pythagoras' theorem, this guarantees that you have to stop in a bounded number of steps. Okay, well, so this basic sort of argument was sort of put in a very general setting by Gowers. I won't go over his statement. I'll just mention that you can view our regularity lemma or decomposition theorem is something in that sort of spirit. So okay, so here's what we do in the setting of matrices. So in the setting of matrices, we can stick with the set of cuts. So these will be our so-called test tensors. Now, rather than the cut norm like this, where you test against cuts, you just take the largest inner product against the cut matrix. We do something a bit different, where we take the soup of this inner product with a test tensor, but we scale it with the size of the cut matrix. Now, you can't just scale by the volume, so it's sort of the product of the number of vertices in U and vertices of V, because then, you know, if you shrink down too small, then you'll see big differences. I mean, if one entry is 0 in one and 1 in the other, then you'll get a big difference. So you need some thresholding. So we'll go down to some cutoff scale that we call N0. So we say that this that we quantify the size of a cut matrix by something like the volume, but we threshold out. We have a threshold N0 for the number of vertices of a factor.
Sorry, on the previous page also there was a norm with star, but it was something different. Yes, yes, here F and star.
Oh yeah, this I didn't. I wanted to skip in the interest of time, but this is star in the usual sense of a dual norm.
Oh,
So it's
okay.
just a dual norm. Yeah.
Thank you.
Yeah. And we'll have a similar use of star here. So okay. So here, this isn't really a norm. It's some measure of the size of a test tensor. But then we define. So this you can check is actually a norm, and it's defined via duality. So this is just a way of getting a dual norm from something like a norm. Okay. All right. And so this cutoff scale is motivated by these clique and hub constructions. You can think about, well, if we're going to try and detect a clique or a hub, what do those cuts look like? So a clique, you can think of, it'll be detected by a cut of this form, so just the indicator of a vertex set with itself. And as I mentioned, in order to achieve a large deviation at the correct scale, this needs to be on n times p to the delta over 2 vertices, and that is above our cutoff scale. So cliques are large with respect to this cutoff scale, and that test tensor would just, its size would be quantified by its volume. But then a hub is a sort of a lopsided type construction, where you have one small dimension and one very large one. And there, in particular, the small dimension of this test tensor is of size np to the delta, which is below our cutoff. And so there you wouldn't take the volume, you would have that the size is somewhat larger in the sense of this B norm. Okay, and then so for this so-called B star norm, we have a decomposition theorem that looks, so I've stated it in a way that's similar to the Fries-Kahn statement. It's just a bit more technical. So okay, so if we assume some growth on n times p to the delta plus 1, so p can't decay too fast, then outside of an exceptional set of small measure, every adjacency matrix can be decomposed into two pieces, a structured piece and a random piece. The structured piece is a combination of not too many cut matrices, where we can control the total size as measured in the B norm. So you don't need to think about what these bounds actually say. It's just, we have the right sort of control on it. And the remainder is small in the B star norm. And this turns out to be the right scale that we want in order to detect these localization phenomena. Okay, as far as the proof goes, it's again an energy increment type argument where you sort of keep adding in cuts. But the point is that that's sort of you can think of that as a sort of algorithm, and then you know you're guaranteed to stop at some point. And basically, if we're allowed to exclude a very tiny set, then we can show that this algorithm will stop much sooner than in the worst case. Okay. All right, so this is a decomposition theorem for these norms, and then we have a counting lemma to go with it. This is very similar to the one for the spectral norm, and it basically says that if you're on a convex set that has small diameter in the B star norm, and you have some reasonable control on the number of homomorphism counts for all subgraphs, proper subgraphs of some point in this set, then these functions are well behaved on this set. Just a few comments. So one, this is a deterministic statement. I didn't cut out any event here, and there's no Erdős-Rényi measure. The proof goes by the induction on the number of edges. So I sketched for you the proof of the usual counting lemma in the case of triangles. And you do basically the same thing where you telescope it. But then what you can do is once you have these sort of test tensors that emerge, you then substitute the control you get on subgraphs and on the diameter of your set, and this sort of gives you a bound in terms of counts of subgraphs, and so that's you sort of use inductive control. Okay, and this here, this is the exact same statement for hypergraphs. I just need to tell you what the B star norms are in that setting. Okay, all right. So so for hypergraphs, so let me just say, I'll just have time to say some results. So we started a bit late. Maybe how much do I have? Maybe 5 minutes.
Sorry, I'm muted. You have 5 minutes.
Okay, all right, that'll be fine. Thanks. Okay, so what can we say about hypergraphs? All right, so an Erdős-Rényi hypergraph. So we think about our uniform hypergraphs. So we still have the vertex set, which is just 1 up to n. But now edges are hyperedges, which are sets of R vertices. And each of these will appear independently with probability p. So this is the so-called Erdős-Rényi R uniform hypergraph. And we want tails for sub-hypergraph counts in the sense of homomorphisms. So this is the same definition as before. Well, it's actually, yeah, verbatim exactly the same as it was in the graphs case. Okay, so there's been some work on this. In this work of Lubetsky and Zhao, they followed the Chatterjee-Varadhan type large deviations approach. And in the dense case, they were able to get tails for the case that for counts of linear hypergraphs. So when you're counting linear hypergraphs, so a linear hypergraph is a hypergraph where all of the edges have overlaps of size 1. 2 graphs are sort of the usual graphs are linear, for instance. Then it turns out that the usual Fries-Kanon type regularity lemma or decomposition theorem, it generalizes in a very straightforward way, and you can do the same stuff. Okay, and then more recently, Liu and Zhao looked at the sparse case, and they were able to get the sharp upper tail in a certain range of p for the case that you're looking at cliques, or a certain other hypergraph that I'll show you in a moment. Okay, just before showing you the results, it's natural to pause and think of, you know, in the graph setting, we had these planted clique and planted hub constructions as sort of obvious ways to create a lot of extra copies of H. And so what would be the analog of these for hypergraphs? So there are multiple such, so you get more than two. So here, here I'm just sketching what happens in the case of three graphs. So the blue here is just sort of a sketch of the adjacency tensor. And then in the colored part, you imagine a sort of planted set where it's all ones. So this is sort of the three-dimensional version of these sketches of clique and hub matrices. But now you see, you know, rather than two possibilities, there's three. So you know, what do you? So Liu and Zhao call these one hubs, two hubs, and three hubs. Okay, and technically you have to symmetrize the matrix, but then that would make this picture kind of incomprehensible. But you can see a one hub has sort of codimension one in some sense. And then a two hub has codimension two, and a three hub is like, well, is a clique. Okay, so these are sort of, you can guess that these kinds of structures might be the optimal ways of creating a lot of extra counts of H. And they were able to show this in some cases, though interestingly, it turns out that you have to sort of broaden to allow the dimensions of these boxes to have different dimensions. Okay, so with Hui and Amir, we got we have a general result about the joint upper tails for homomorphism counts in their Discrete hypergraph. So this is so he basically stated this theorem in the case of graphs, but it carries over to hypergraphs. And we have this. So this is a non-optimal range of P. So it would be nice to improve it. We do have so our B star norms are sort of customizable in a way that I don't have time to describe. But for certain types of graphs like linear hypergraphs or sunflowers, you can sort of adjust the B star norms to get this down to 1 over delta. Okay, or even further, but then it's just only the upper bound holds. We don't have a matching lower bound. Okay, and then so our result.
Can you return to the previous for a minute? Lower bound. Aha, the wider range. Thank you very much.
Okay, yeah, sorry, I was going a bit fast.
Thank you.
So in their paper, Liu and Zhao solved this entropic optimization problem for the sparse case, and the case that H is a clique. And so when you combine with their results, you get this this explicit formula for the asymptotic upper tail. And you just, you know, you don't need to think stare too hard at this expression. The point is that it's just like in the graphs case, it's a minimum of two expressions, one that comes from a so-called R hub, which is a clique, and then the one hub. So in the case of counting cliques, it turns out that the best thing to do is either the sort of full codimension hub or the you know, it's the two extremes. You don't have the one in the middle. But they were able to exhibit one graph where that was not the case, where they got a sort of the optimum was sort of attained by these sort of boxes of intermediate dimensions. And so, okay, so it's this graph here. So this is a linear hypergraph where the line segments here are the edges. So you have 4 edges and 6 vertices. And they got the upper tail for this. And this, they were, you know, it was, I mean, basically what they saw is that the problem seems very difficult in general. And this was sort of the smallest case that where they got a different answer from what they got in the Clique's case, but it sort of remains to see the bigger picture. But they have a very nice argument that maybe indicates a way forward in terms of this specific example. Okay, and then I'll just very briefly mention what I won't write down. I won't say in much detail, but we need to, those previous statements I gave of the decomposition theorem and the counting lemma in the matrix setting, they're basically the same verbatim. In the hypergraph setting, I just need to say what I mean by test tensors in the B star norm, and what we take for our sort of class of test tensors is just Bernoulli tensors, which you can write as products of tensors of lower dimension. So they're, in general, they're not boxes, is the point. So a box would be if all of the factors had dimension 1. So they can be interesting on, say, r-1 different coordinates. Okay, so the cover of Gödel-Escher box indicates that this is a depiction of a test tensor. So you sort of specified the marginals here, the 2-dimensional marginals of this 3-dimensional set. Okay, and then we have an appropriate way of measuring the size of a test tensor, where the key is you have to attach appropriate weights to the factors in order for the counting lemma to work. All right, but there's sort of, and I'm not showing the most general version of these norms, but so one of the points of this whole theory is that in the sparse setting, you can't sort of use one topology or one norm to study everything. You kind of have to be willing to change your norm depending on what you're interested in. And so what we actually give is this family of B star norms where you can choose the factors based on the neighborhood structure of your graph, and then also adjust these weights. So it's sort of user specified norm, set of norms that you use. Okay, but thanks for your attention. Sorry for the hiccup.
Thanks a lot, Nick. Are there questions or comments? Please write either in the chat or unmute yourself.
Sorry, Bernoulli tensor is the tensor product. What is Bernoulli tensor?
Just 0, 1 entries.
Huh? Bernoulli test tensors. Tensor which is a product. What is Bernoulli?
Yes,
Huh?
well, so these generalized, these cut matrices are an example of this. So yeah, so when I say Bernoulli, I just mean the entries are 0 and 1.
And tau be a Bernoulli tensors. What does it mean, Bernoulli tensors?
Pardon, I didn't catch.
Huh?
Can you ask again? I didn't hear part of the sentence.
The question was about the coordinates, I think, of the
word Bernoulli
the
tensor is a simply product of tensors. So what is it?
Right. Okay. So I guess, yeah, maybe this is ambiguous. It's, say an entry of this matrix is given by the product of entries. So you're doing an entry-wise product of tensors here.
Hmm?
So this is a product that's an entry-wise product.
Hmm. Thank you. Is it the same as a product of one coordinate dependent tensors, or what is it formally?
Yeah, so for instance, this could be the so this will be a tensor, but it only varies on a subset of the coordinates, so it only it's constant in some directions. So
Thank
just
you.
like in the case of cut matrices, say this would be a 2-dimensional matrix, which is just say a horizontal stripe, and then you multiply it by another one that's a vertical stripe, and that gives you a box.
Thank you.
Okay, further questions? Doesn't seem to be the case. Let's unmute ourselves and give an applause to both speakers. And maybe Nick and Amir, you can send the slide.